Greetings everyone. In this video lesson we're going to be talking about creating vector data. Students very frequently ask me, where do I get the data? And that's a great question. Fortunately, of course, there's an increasingly large quantity of GIS data that's being put online. However, GIS specialists often have to create their own data, so this is a very important topic. The joke kind of goes that there's all this data out there, and yet none of it is exactly what you need. So we always end up having to make a lot of the data ourselves and construct our data sets ourselves as GIS analysts. So first off, when you're searching for GIS data online, it happens to be the case that we don't really have a great way of searching the internet for GIS data right now, at least at the time this video is being recorded. You might be looking for shapefiles about a particular region of the country, but the standard way of keyword matching, as sophisticated as it is, and which serves as the foundation for many search engines today for document search and retrieval, can't go in and tell you that there are certain GIS data sets available for download on certain sites. Instead, you're hoping that someone has put the necessary keywords on a website that's next to the data that you can download on the page. That way, when you search for the particular keywords, that web page comes up and you can download the data. There are GIS web portals that you can find that have been set up for different places. Cities, counties, sometimes even states will put up their own GIS web portals for distributing their GIS information, but that's still not overall standardized or overall centralized. You have to find them kind of on a one-off basis. And then, of course, if you do find that, and you do find the data that you're looking for or think that you have, then, of course, once you download it, all of those issues about data quality and the kinds of representation that we've been talking about a lot in the last few videos really start to come into play. Just because you can download it doesn't mean that you should use it. And it doesn't mean that it's appropriate for your project anyway. It may be completely unusable to you, even though you thought you had found something that you could use. It's fantastic, of course, when you can download exactly the data set that you need and it'll be up and running for you, but you very often cannot count on this, so we end up having to create our own data. That's an important skill as well in GIS proficiency. It can be a very time-consuming part of doing GIS analysis. So it's very important that you budget your time when you're implementing a GIS project so that you have enough time to create the necessary data or maybe modify an existing data set to your needs and still create or still complete the project on time. Of course, it can also be very financially demanding in order to create GIS data sets, especially if it's going to require field work, travel, field data collection teams, and so forth. So never underestimate the amount of time it's going to take you in order to get your data downloaded, modified, created, whatever, prepped for your analysis. Be aware that that's a major time-consuming and potentially financially consuming part of doing GIS. There are only a few ways in general that you can create vector GIS data, and most of them fall under the general heading of digitizing. And there are two major ways that you can digitize when you're in the computer lab. Tablet digitizing and heads-up digitizing. Heads-up digitizing is often called on-screen digitizing. I think I call it on-screen digitizing a lot. Tablet digitizing is used increasingly rarely today, so I'm not going to spend a whole lot of time on it in this video, but in either case the principles of the digitizing remain basically the same. In both you're going to have, in both of those cases, you're going to have some kind of hard copy map that you want to get into the computer. And even though we're increasingly living in the digital world, of course, there's still, at the moment, a bunch of information, a bunch of legacy geographic information that's still held in hard copy maps that have not yet been entered into computer systems. You may very well find yourself in a situation where you need to use data that can only be found on a hard copy map, especially if your analysis is including a historical component. There are lots of historical maps that contain lots of great historical data that are not in ready-to-use vector GIS format, so you're going to have to digitize those maps. If you're using the tablet digitizing technique, then what you do is you sit down at a large tablet, a large table looking thing that's connected to a computer, and then carefully attach the hard copy map to the tablet so it can't move around. You often tape it down with masking tape on the corners or something like that. Then you use what's called a digitizing puck, which has a crosshair on it, and then you go around and register the coordinates of the map inside the computer system, clicking on a point, telling it what that coordinate is, clicking on a point, telling it what that coordinate is, and then once you've registered the whole map, or registered often what it is the corners of the map, so the computer understands what area you're going to be digitizing in, then you can use the puck to go around and click on the important points that you want the computer to save into your GIS file, and have the computer create either points or lines or areas as you're going around and clicking on the map. More common today is the use of the heads-up or on-screen digitizing technique, in which you scan the hard copy map. When you scan the map, then you go through a process of geo-registration. You geo-register the scan. And we're going to talk more about geo-registration specifically in a later lesson, but it's basically the process of assigning the coordinates to the scan so that it can be geo-positioned. So if you scan a map and then you bring it into a GIS software package, you can't expect for that map, that scan of the map, to just appear in its correct geographic position. You're going to have to go through a geo-registration process where you tell the computer where certain points on that scan are on the Earth, and then the computer will be able to correctly geoposition the scan. Once that's done, then you can create vector data by clicking on the screen, using the right tool of course, to create either points, lines, or areas that you'd like to create. Effectively, you're drawing over that scanned map. It may be the case that the GIS laboratories that you're in now no longer really even have physical digitizing tablets available, and so everything is done on screen. One situation, though, where the tablet digitizing still has an advantage over the on-screen digitizing is because it's very frequently the case that the map that you're trying to digitize is larger than 8.5 by 11. You can have very large map sheets. And so you're going to have a very large format scanner if you're going to scan the map and then use heads-up or on-screen digitizing techniques. It doesn't work terribly well if you have one of those little 8.5 by 11 flatbed scanners and you're trying to put different pieces of it onto the scanner and then try to geoposition those and digitize it in pieces. That really doesn't work terribly well. So if you have a very large map that you need to digitize information from, then most digitizing tables and digitizing tablets are designed to accommodate very large maps. So that's still one advantage that they have in a situation in which the table tablet digitizing is still used. But either way, when you're creating a vector data set by digitizing either on a tablet or on a screen, there are several things that you need to be concerned with. And this is because GIS is very much a garbage in, garbage out operation. When we get to the discussion of how to solve problems and how to answer questions with GIS, you're going to very quickly find out that it doesn't matter how well thought out your procedure is or how theoretically perfect your methodology is. If you have bad data, then your results are going to be wrong. You're not going to be able to get the correct result. So it really pays off to take the time and be very careful about the creation of your data sets up front. If you start to get sloppy when you're creating your data, then you're going to end up with incorrect answers, regardless of how careful you are in designing your methodology just to be perfect. So don't introduce errors into the data, because if there's errors in the data, the answer, the solution, is obviously going to be wrong. So how can errors be introduced into your data? When the vector data sets are created, it's a great idea to choose the scale at which they're going to be created, and the scale needs to be communicated in the metadata of the file so that people know which scales are appropriate to use that data for or at, and which it is not. So that also means that you should choose the scale at which you'll be digitizing the information and then keep that consistent across the entire digitization project. A single feature class shouldn't have different parts that are digitized at very different scales. I mean, of course, you can zoom in and zoom out a little bit as you need to, but you don't want to digitize them at extremely different scales. When you're digitizing information from a hard copy map, the scale of the digitized file that's produced is going to be the same as the scale of the hard copy map. So if you're digitizing information from a 1 to 24,000 map, then the resulting data is also going to be appropriate for use at a scale of 1 to 24,000, and that needs to be reported in the metadata. I can't do analysis at a scale of 1 to 1,000 using data that was designed from a map or digitized from a map that had a scale of 1 to 24,000. Maintaining this consistency is generally very easy when you're doing physical digitizing on a tablet because you can't zoom in to your hard copy map. It's at the scale that you see it when you're clicking the puck, and then that's just it. So that's the scale that gets reported. However, when you're doing heads-up digitizing, it is easy to zoom in or zoom out if you think it's necessary in order to get a particular line or a point positioned exactly where it should be positioned. That's okay to an extent, but if it goes to an extreme, it's not going to be in your best practice. Instead, you should still view the scanned map on the screen about the same scale as the map was produced, and so all of your digitizing is done at that scale. You're not going to be able to get more accurate by zooming in than the data was created on that particular scale map. Sure, you can zoom into a digital scan on a map all you want, but for instance, think about what happens when you zoom in to a line. You're going to notice that there's going to become a large amount of uncertainty about exactly where all of the different features are located because of the size of the symbology that is used to depict them. So once you zoom in past a certain level, it doesn't help you to create a more accurate data set because of the limitation of the source map. Think about zooming into a line that represents a thick line that represents a highway on a map. Okay, where is the highway? Well, the symbology itself is taking up space, and then it's going to get a bit fuzzy because of the different pixels of the scans, and so there is a limit to the accuracy of your digitizing based on the accuracy of the map. And when you're zooming in and working with the data and zooming out and trying to get something digitized, you may notice that there may be ways that the representation of the features may not be completely accurate anyway because of cartographic generalization. Sometimes smaller features are all fused together into a larger feature area on maps. For instance, in certain circumstances, if there are lots and lots of little lakes or ponds in a particular region, in a data file or on a map, they may fuse together, so it appears as though there's just one large lake there. That's cartographic generalization, and it is an okay cartographic technique to generalize like that, but you have to be aware of that when you're digitizing data, that cartographic depiction may not be the absolute ground truth of that particular area. So if you had the generalization on the map, when you digitize, you have that generalization in your data set. In other circumstances, the little lakes that may have all kinds of inlets or outlets and a very detailed, complicated shape, but on a certain scale map, they could be simplified. You might not see all of those ins and outs and little crevices of the map. You might also find that some features have been completely omitted. For instance, some smaller lakes at certain scales may not be large enough to even register, to show up on the map that you're digitizing. So if you have to be aware of these issues, or you do have to be aware of these issues when you're digitizing data from maps. For example, if you're capable of digitizing a map within 0.5 millimeter of the position shown on the map, and you're at a scale of 1 to 24,000, this error may be about 12 meters. But if you're digitizing a map with a scale of 1 to 1 million, and you're able to get that close, you'd be looking at an error of about 500 meters. That's why it's important to be sure that when you're using a data set, that you are using it at the scale at which it has been created, and you're analyzing it at the scale that's appropriate for you to be analyzing it. If you're using data that was created at that 1 to 1 million scale, potential error of 500 meters, you can't zoom in and try to make a conclusion based on that data that is more accurate than that 500 meters. I also want to give you two other very important kinds of errors in digitizing, and these are overshoots and undershoots. An undershoot occurs when the digitizer doesn't completely connect a line that should connect to another line during the digitization process. Oftentimes, the digitizer may be able to get the lines close enough so that they appear to the human eye at a certain scale as if they connect. But that's not good enough for the computer and computerized analysis. Computers are painfully literal, and if you're digitizing two roads that are supposed to join together at a T intersection, but the digitizer has introduced an undershoot and for this connection, and so they're actually like this, even if it's just a very small distance that they don't connect by, maybe inches, maybe even. Then the computer will not understand that they're supposed to connect and won't be able to recognize that connection. This can be extremely significant in operations such as network analysis and routing, where you want the computer to really understand all of the connections that are present in the roadway system. Overshoots are another problem. Overshoots are sort of the opposite of the other problem. Overshoots are when the digitizer jumps over the connection that was supposed to be made. So in the case of the T intersection, this would be an undershoot. But if I were to overshoot, it would look something like this. So rather than coming together nice and neatly as they should, one line overlaps the other. And then depending on what method is being used to establish the topology of this data set, the computer may still not understand these roads connect, but may think that they lie on top of each other, or it may be interpreted as a line that defines part of a little road that's on the other side that shouldn't be there. Either way, these are problems in your data set, and they're going to make your analysis wrong, even if your methodology is great. How can you prevent something like an overshoot or an undershoot? Well, one function that you can use to assist you during your digitization operation is called snapping. And snapping is used to help reduce undershoots and overshoots. Essentially, snapping allows you to define a particular distance at which 2 points should be considered the same point. By recognizing that you need to make 2 lines connect perfectly on a vertex, it may be very difficult to get that to happen. If I'm really trying to make sure that I've got 2 lines or 2 edges of a polygon or whatever that immediately or directly line up on a single vertex, it may be very difficult to click on the exact same point twice. So recognizing that, we could set a snapping tolerance. And this snapping tolerance says that as long as I get my mouse, when I'm trying to do this digitizing, within a certain distance of an existing point, then the computer should treat it as if it were on that point. So if I'm trying to get back to this point, and I accidentally just put the other line here, if it's within that snapping tolerance, it will snap and make it that one point to make sure my topology is very clean. Another way of thinking about this snapping tolerance is that minimum distance, or the minimum distance that is allowed to be between 2 different points. Whether these points themselves are vertexes of lines, or of areas, or parts of 2 different lines or areas. Anything less than this distance, this snapping tolerance, becomes the same point. Snapping tolerance is definitely your friend, and setting it correctly for your particular project is important. It is really going to help you out. It can dramatically reduce the number of overshoots and undershoots that are in your data set if you correctly use snapping. It's really going to help you create completely closed polygons or areas, and it's also going to speed up your digitization process. Most GIS software packages will allow you to specify a snapping tolerance while you're digitizing. So it's an important function to get familiar with inside your particular GIS package. Another point about creating vector data is that when you're digitizing areas, it's very important to ensure that you don't have slivers or unintentional overlaps. Okay, so for instance, in this situation, we might have two different areas, and these may represent zoning areas in a city or congressional districts. In cases like that, zoning areas, congressional districts, other political territories, they're intended to share the exact same boundary. They're intended to come up right next to each other, and there shouldn't be any gaps between them, and there shouldn't be any overlaps in the areas. I mean, think about that. If you've got congressional districts, they should line up directly. There won't be any gaps between congressional districts, and there won't be any overlaps between congressional districts. But if they've been digitized poorly, there could be very, very, very small gaps between the two polygons, and this would cause problems during your analysis. And likewise, if someone has digitized it poorly, there could be very, very small overlaps of two different areas or polygons when there technically shouldn't be. And again, this is really going to mess up your analysis if those are present when they shouldn't be. So different GIS software packages also have tools to assist you in creating area features that share boundaries perfectly but do not gap and do not overlap. It's very important to make sure that you know about these tools and also you use them in order to preserve the integrity of your data sets when you're doing digitizing. Unfortunately, when you're downloading data, it's very common to get data that has not been created using these tools and using these functions, and so it doesn't have the geometric integrity that it should. And if that's the case, you're going to have to spend time cleaning your data and improving your data in order to get it ready for analysis. Another way that you could introduce errors into your vector GIS data is by making errors when you're entering information into attribute tables. Oftentimes you'll have to type in information into an attribute table when the digitization is taking place, and there are a number of ways that errors can creep into the GIS data simply from entering mistaken information due to typographic errors or some other kind of error. And obviously, if you're doing something like selecting information based on the attribute, it's important for all of those attributes to be correct. So it's another important thing to make sure that you have correct, and different software packages have different ways to help you accurately enter attribute information into a data set as it's being created. This can also be a very time-consuming thing to do, so using different functions that your GIS software packages have to speed you along, do it faster, do it more accurately, are very important. Often these involve setting some kind of default value for a particular attribute field, or ensuring that attributes can be selected or must be selected from a list of acceptable values rather than allowing the value for that cell in the attribute table to be entered free form every single time. You don't have to type the same word 1,000 times if you can make it a default value and make sure that it's typed correctly once and then entered into a bunch of them. And then likewise, you don't want to have to type a whole bunch of other words if it can only take on 4 different values, and you can put a drop-down list into the attribute table so you can select from the drop-down list. Make sure there's no entering something that shouldn't be in there or any typographic errors regarding what is in there. When we begin to talk about geodatabases in later courses, there are other techniques that we can use with our vector data that are database specific, geodatabase specific, that will help you to ensure both the integrity of the geometry in your data files as well as all of your attribute information. So actually, geodatabases in general, one of the ways that they really, really help us out is by making sure that our data, both geometry and attribute information, is correct and clean. And they provide a lot of tools to do that. So we will definitely get into geodatabases in other courses. But by the way, I would also like to say that vector GIS data can also be created through field digitizing. And field digitizing can be a lot of fun. That's when you go out into the field with GPS receivers and you collect points and you're digitizing vector data sets as you walk around in the field, often with the GPS antenna and the GPS equipment. And you're often also entering attribute information at the same time, maybe into some type of portable computer, a laptop, tablet, even a phone, when you are collecting information and you're right there in the field. That's a lot of fun, great way to collect a data set, and we're going to talk more about how to do digitization using GPS receivers in the field, but that's going to have to be a different video lesson. Finally, I guess I should mention that you can also create GIS data programmatically. Here again, this particular video series isn't going to be concerned with GIS programming. We'll have to get into that in another course as well. But I'd like to go ahead and include that on the list so that you know that it is an option for creating GIS data, so that you know that it's possible. If you have points and you need to turn them into lines or turn them into polygons, you can do that without having to go and manually digitize everything. You can write computer programs that will create the data automatically and also even fill in attribute information for you. So that makes you very efficient and really speeds along the amount of work that you can do if you can do that programmatically. Well, okay, I think that's about what we need to know right now about creating vector GIS data in theory. So I will see you in the next lesson.